Okay. Divide intervals into minimal numbers of groups. Intervals left-right represent an inclusion interval. You have to divide the interval into one or more groups such that each interval is exactly in one group. No two intervals in the same group interact each other. Return the minimum of the group you need to make. Okay, so right, so first find the minimum group such that the interval cannot intersect. So actually the idea is just use line sweep. Compute the maximum interval overlapping count. Okay, so count interval, add interval, and this value minus the interval here. So max row group alter time state and the count. Maximum row, max row. Okay, that's it. String 1. Optimal partition of string. Given a string, partition string into one or more substrings such that the character no letters appear in single-digit order, right? Okay, so minimal, right? So what it means? Right, so actually it's the maximal count here. Oh wait, not the maximal count, so we just greedy these 2 pointer. Find the minimum partition such that each group only has one leader. Alright, so use hash table. Idea is use the hash state here as a 2 pointer. 2 pointers. So now basically it's group. Right, so we also have visited. So if visited count C, that means we need to use a new group. So group, we add 1. Most frequency event. What it means event element? The event, event is the number is event. 0 to first here. There is a type return the smallest one. Okay, most frequency event. So goal is find the most event and smallest. Okay, so actually just idea is that record the event frequency. Insert. So okay, so if this is event, means we can add this. Use a vector to calculate. Okay, so maximum frequency and smallest element. So we sort. And based on the equal to otherwise, insert maximum. Right, that's it. Alright, so longest increasing subsequence. You are given the integer race and the k. I want to find the longest subsequence that meet the following requirement. The subsequence is greatly increasing and the difference between adjacent is at most k. Oh, okay, so idea I want to use is dynamic programming to do that. Find the longest subsequence such that adjacent value difference is at most k. String increasing errors. Okay, so need to be string increasing. What we want to do here is that consider about the brute force approach. Can ask a dp. dpi is the maximum length of lis. Okay, and so consider brute force approach is that we can try to do element. Okay. dpi is going to be 1 and dp is maximum dpi dpj at 1 if the nonce I is greater than nonce j and the nonce j minus nonce is smaller than k. That it's the brute force approach, but this will be linear and square, not linear. So I want to improve to linear or envelope something too slow. Okay, too slow. So now you are trying to find out that okay, so prefix so far here that this value is smaller, and this value cannot be greater than k, right? So greater than k. So alright, so this approach, this means we cannot be equal, and then we should find the first. Alright, so maybe I can use this value because the constraint it's 10 10 power 5. Actually, this condition doesn't matter, right? So we can just try to find out that non-equal. We can find a non-equal and smaller than this value and the maximum, and at most k here. So actually, it's considered the DPI is maximum of the first number at 1. So this can be actually this condition is no use. So how do we handle this? The difference should be smaller than k. We can maintain a sliding window, but it's hard to think. It's that so for each value, we just calculate the okay, this condition is that numbers is smaller than it's greater. It also can be this. So I want to find this value that should be greater. Okay. They cannot be equal, so wait. K is 1, right? So right, I think they cannot be equal, so um, yes, currently no idea. But actually, it's very classic problems here. If we want to maintain the first K, you just try to if we can compute the such this to one side. So we need to find out that if there is the value and the maximum where we minus K. So it's nonce I minus K, nonce I minus 1. So in this range, this can be used as this range, and they cannot be negative. So I want to find the maximum prefix. Maximum. Okay, find maximum of this segment. Alright, so it's a segment, right? So it's segment. Maybe I can use segment tree to do that. Yeah, but how do we do? How do we handle the segment tree? So we can get a maximum queries here. We may also have update queries. Okay, so we are seeing that, for example, 4 means that the value for the longest increasing sequence is equal to 1. Okay, actually the J, this doesn't matter. We only consider this value. So we can try to do here, it's we can use the same tree, consider to left and right. Alright, I have an idea. Maybe use segment tree to query maximum, and use and update the maximum. Right, so I want to use segment tree. So max is element. Right, so segment tree, this is the maximum interval tree. Alright, series size I want to use 4. The big from index yeah, and left right. Index is 1. Maybe we should use 1. 0 to maximum. No, here. So right, we don't need to build a tree. Actually, initially it's going to be 0. We just use update. We want to update which I to current index, and secondary position is equal to secondary L is equal to, or position is equal to X, and return it. The segment, this value is maximum segment. Two and three. So 1, 2, 3. That's it. We're gonna need. We only update half tree. So if this is half, is 0, 1. The position is 0. Say mean. Mean is going to be 0. And it should be position. Update the left tree. Update left. Otherwise, update right. Update left, update right. Okay. So update. And what about query? Query. Alright, so find this range. Alright, so use segment tree to update this and query this maximum, right? So 5 maximum. So next it's want to query right, so means maximum interval. Want to query 1, 0 max. Current range is x minus k, x minus 1. This cannot be negative, so maybe that is going to be 0. Alright, so almost k here. Find this range. Find this range, this interval. And we update this position and the maximum interval at 1. Right. Okay, this can be used segment tree. Now query this. We're saying that if this interval is too small, right, let's consider the base case. Base case I need to be sync, but currently I just try to update the left and the right. So left is going to be query just query this to null. And what about if this range, it's return this segment. If this interval is in LR in RR, right? So if impossible, what is impossible? If the this segment is too small, or this segment is too big in the segment right. So it's too big or too small, right? So we need to build trees and multi-arrow. What? The tree height, why is that big? Sine go over 4. Why is that big? I need to think. If this is the end node here, and this. Why? Wait, I need to think. If this 151 is going to be 1. Sine go over 4. Okay, x can be 1, right? So x can be 1. S can be 1, and so maximum value 21 is here, and x is. I want to check the maximum interval is success or not, and update current 0 to max. It's LR range, and we update this position. We update this value at 1. Update. Okay. Current is 0. Oh, so in update, if this range is oh wait, if this is smaller than position, it means that wait, if the mid current is 0 and the current position is greater than mid, this is 0. It's not. Should be update this range. Update this range. It's update the wrong range. Wait. I need to sync the segment tree while I'm wrong here. Position is not. It can't be. Alright, so let's see all this range. Okay. So almost 2. I figure out this arrow. So position is too small. Means we should search this value. Otherwise, to meet. Okay, so what's 2. If it's weird. That's weird. It's wrong. This is wrong. It's weird. Yes, made something wrong here. But wait, wait, am I? Let me see. If this range, we are trying to update what? Update this position. And so for this index, if we know this is going to be, just try wrong. For this range, 0 to 5. Currently, 0 to 5, and we want to check out this position 1. And in the mid is 2. So it's 0 to 2. And 2 to 5, right? So 2 to 5. 3 to 5. They cannot be intercepted. Okay, so if position is in which range? Is in this position is 1. This mid is 2. P is 1. Which means this position is smaller than this mid. So we search the left part here. Okay. Oh, okay. Let's lose weight. Right, this should be correct. Took some time to debug. Okay. Oh, waste a lot of time. Actually, I can do faster. I just in this range, I update wrong range. Yes, I want to see my runtime. Alright, it's good. Okay. Waste a lot of time. Alright, let's see the problem. What? The problem one is very simple. We just try to try to find the smallest maximum frequency and smallest one even number. If there is such no such element, return active one. And in this condition, if there have only one, is that if there are all arrays odd, we will return active one. So idea is we just go through the array and we record a maximum frequency event element. We just record frequency here. We record frequency here. If this is event, we record it, and we just sort it. We can sort it by frequency, and if there is the same frequency, we return the smallest element. So this return compare function is if the frequency is the same, we must return a smaller one. Otherwise, we return the maximum frequency here. So now the only condition is that all the value is odd. There is only one condition, is array is empty. So return it. So overall time complexity is n log n here. Okay. Can improve to linear. You can use counting sort to do that. Bucket sort, yeah. That's problem one. Okay, and about problem two. Okay, so in this problem, you want to find out that what is the optimal partition. It's we want to find the minimum numbers of substring such that each substring, the character in each substring are unique. So basically, we can use you can think very the very easy to think idea is that you just greedy. How to greedy? We just from left to right, and if we meet the is character, that means that we must be split in this segment. And actually, the substring size is at most 26. Because Unicode letters only have 26, so the maximum substring actually is at most 26 here. So basically, we just use the set to record busy set, and this time complexity is linear. And if this is count, that means that we must add a group here. So yeah. So we add the group and update it, and push in the visited. Let's edit problem 2 and about problem 3. And the problem 3 is that you are given some interval, and you want to This problem is actually is the same as a meeting room. It's a meeting room, almost the same as a meeting room. Actually, you want to find out that you want to divide this interval into one or more groups, such that each interval is exactly one group here, and no intervals cannot be intersection in the same group. So, a greedy approach is that if we calculate the maximum intersections here, actually we always can use these intersection groups to get the answer, because if the maximum intersection is 3, that means that actually we only use 3 groups, and we can always separate this group to exactly one group, and no 2 interval can be intersection. So the problem just can convert to the try to find what is the maximum intersection in this interval. So you can use line sweep. The same as the meeting room. This problem is same as meeting room. Say Leetcode meeting room. Yes. Find the max meeting room here. So we just calculate the line sweep. This is a common technology. We just add interval left and interval right. Add left endpoint will add 1, and right endpoint will subtract 1, minus 1. So that's the idea. And then how do we update? How do we know the maximum? We just go through the prefix compute, go through the time step and compute the prefix here. So actually you can see the problem almost the same. Yeah. So that's the idea. Okay. So about problem 4 I can do more faster, but took a lot of time to debug. Yeah, with some time. Okay. So this problem okay. So this problem, it's that you want to find the longest increasing subsequence such that it satisfies these 2 constraints. The subsequence must be straightly increasing, and the difference between the adjacent elements is at most k. Yeah, there's a similar question in Leetcode, but I forgot. You just in order to consider the index from left to right, the brute force approach is just for each index we just tried out that. The brute force is simple, right? So brute force is for each index. You just try or nonce j smaller than nonce I, and the nonce I minus nonce j should be smaller than k. You just try all this index, try all j. So this is brute force, and it's actually the LIS. And in the LIS problem, you can convert to the problem to another. You can see the LIS problem is actually almost the same here, and but a little difference this constraint, but this doesn't matter. This constraint is no use, not no use, but you can just use interval idea to do that. So you can see the problem. Maybe you can see the core LIS problem, and how do we solve? Use BIT. It's almost the same idea to do that. So yeah. So now Okay. So how do we use binary index tree? Or actually, this problem cannot use binary index tree because this is the maximum. So we must use segment tree. It's more general in this problem. So how do we do? So first, you need to find the list range, because in this constraint, nonce j, nonce I minus nonce j should be smaller than k. You can generate to nonce I minus k here. You want to find this range. Find range. Find this range. You just find this range because it's almost the same. If there exists this value, that means that this value minus this value is smaller than k. So we just find this value, this interval, and in this interval, we want to find out that what is the maximum increasing subsequence in this values here. So we want to find out the maximum of this segment, and we also need to update the query, and you only need to think is, can we use the segment tree? So segment tree can easy to solve this. Now, how do we use segment tree? And what is a segment tree? And actually, you just record the maximum values in this, and then we can add the interval tree. So root is the mouse, and we also have a log. We will separate to two interval here. This is a segment tree, and each interval we just record what is the maximum. Total maximum dp of this interval. What is the maximum dp of this interval? Yeah. So okay. So this query is query list range. We want to query in whole range, and we want to find out that what is list range maximum, right? So we queried it. So in this query, you just try to go through the tree, because if they have some base case, is that if the this range is cannot be intersection in this range, that must be array return. Otherwise, if we find out that this range and the whole range is in this range, that means we have final answer. We don't need to split. We don't need to split the range. So we just return it. Now we want to split the range to left, right, to left and right. Right, so we split this range to left and right, split this to left and right, and the whole LR is going to L to mid plus 1 to R, and we return maximum, this two value. So that's a segment tree query. And I waste a lot of time to implement my update function because I have some bug. So now if now we want to find, actually we only update, this is update the leaf node. What this means, leaf node? Leaf node is L is equal to R. The range is 1. The range is 1. L is equal to R. We always say this range is equal to 1. So this is a leaf node. So if this is a leaf node, we just check out that. If the position is the same, we update this node. Right? We update this node. And you need to care for how to how to update a tree, you need to be careful. For example, position is 1, and current range is 0 to 5. So we get a mid. We can use the mid to determine the tree we need to update. If this is lying in the left range, we update the left tree. Otherwise, we update the right tree. We cannot update. Actually, we don't update. We don't update both because we only have one direction, such as the binary search tree, right? So we only have one direction, and actually, after we update leaf, we can go through from leaf to root. We go through from leaf to root. We have a lot of interval, and now we can update from leaf to root here. How to do that? In this, get information from child. This is important technology to solve this problem. So yeah, that's it. Yeah, so waste a lot of time. You need to care for if you find out the mid, you need to check that. Okay, so the position is in the left part. We update the left. Otherwise, update the right part here. So that's the idea. Okay. Right. So. Okay, that's it. Okay, and this problem, what about if maximum is up to, how to solve this if the maximum of the numbers is up to this very big value? So you can use sparse segment tree. We can use sparse segment tree, or we can use convert numbers to 0 and -1 here. We can use this technology to do that. Yeah. So it's the follow-up. I think it's the follow-up of this problem. Follow-up. Yeah. Okay. So that's the idea. Okay. So this is segment tree. Quite only 300 people. It's weird. You can see final scoreboard. You see Taiwanese people in the leaderboard. It's weird. Really? You have Taiwan. So like, okay. Oh, I see. Yeah, it's good. Nice. Only one? Okay, so now one. That's very fast in 8 minutes. So fast. Alright, so it's my today's contest. Okay.